open science, but that doesn't just mean open as in transparent. It means open to people, and it's quite difficult because you have to refer to people as non-scientists as if that's some kind of weird disability, but it's not. It just means that anybody really can access science if it's nicely explained and interesting. We've been going for about 5 years, and we were hosted originally in a wine bar. And that sums up really part of the ambience. So if you haven't already, then part of the Cafe Sci experience, the clue is in the name, cafe. So cafe means you have a drink. It doesn't have to be an alcoholic drink. It could be a cup of tea. It could be a coffee. You can have a glass of water, if you like. You can have an ice cold limoncello, a liqueur, or you could have a whiskey. I'm going to go with the wine to start with. I won't drink the tea because I don't drink tea, but I'll work my way through the rest later on. The idea really is that you're in a cafe or a bar, and Ken Rice, who's our speaker today, has just stood up and someone's shouted out to him, "Ken, tell us the one about exoplanets and Earth's climate again." And that's what Ken is going to do for us. Before I get round to introducing Ken properly, though, there's a little bit of admin I need to go through. So first of all, you should all see, probably on the bottom of my screen, I see some buttons, Q&A. If you click on that, it allows you to pose a question. That question will come through to us, the panelists. And what will happen is I will look at the questions and then I'll interrupt Ken at an appropriate moment shortly after you've asked the question to put the question to him. And if it's something that's complex or I feel you might want to speak, I might invite you to become part of the panel very briefly and go on video and put your question in person. Otherwise, I will read it out. There's a chat button, and the chat allows you to send a message to the panelists. And that's really if you, oh, thank you, Avril. Avril says, "I'm very impressed with your range of drinks, Chris." And so am I. That's quite good. Sarah wasn't as impressed as I was. I said I wasn't going to drink them, but I lied. So the chat button allows you to send a message to the panelists, and that will particularly go to James if you've got any kind of technical difficulties. And somewhere, I don't see it at all, but somewhere you have something which is to raise a hand, and the raise a hand is just to make an interruption. Well done, Avril just did that. And it's also the way that we give a round of applause at some point. Okay, that's much ado about nothing. Ken Rice is a lecturer at the University of Edinburgh, and he tweets most of my, or many of my Cafe Sci panelists and speakers I initially met on Twitter. And it's really nice actually, because you get to actually meet people or hear them talk on a custom way just for me, well, and you people as well, on a topic. And Ken tweets a lot about climate and climate change, but actually his study is in exoplanets. That's planets that are not around our solar system. And of course, I suppose people are very interested in the climate of those. And so Ken also has a lot of knowledge about Earth's climate. So without more ado, Ken, if you're ready, James will spotlight you and hand over to you, and we'll welcome Ken Rice to talk about exoplanets.
Thanks, Chris. Yes, I've got a few slides. As Chris said, I guess we met on Twitter, and most of my social media has been about sort of science communication, and in particular, you know, climate science, climate change. But my sort of professional research is on sort of computational astrophysics, but mostly focused on planet formation, and in particular, sort of exoplanets. So I thought I'd start with, and if I can just find it. Let me find. Yes, there we go. Go to the beginning of that. Sorry, get myself sorted out here. So I've got some slides. All the slides coming through all right? Yeah. So as I said, so I thought I'd do a few slides on exoplanets, and then I can sort of do a few on Earth's climate, and or we can stop in the middle. So as Chris said, exoplanets or extrasolar planets are planets that orbit stars other than the sun. And as of this morning, when I checked the database, we had 4,266 confirmed ones in just over 3,000 exoplanetary systems. And that tells us that, a good 600, 700 of these systems have multiple exoplanets in them. So we're aware of quite a lot of exoplanets, and we're aware of quite a lot of systems that are multiple planet systems, which of course is interesting. We aren't as yet aware of any, or maybe there are a couple that might be similar to the solar system, but that's probably partly because of the difficulty of detecting solar system analogs rather than them not existing. So it's easier to find planets that are closer in or that are bigger. I'll go through that in a minute. And I guess the sort of obvious maybe way of finding planets is just to, oops, gone too far, is just to stare at stars and wait for something to pass in front of them. And so this is known as the transit method. You just stare at lots and lots of stars and you wait to see if something blocks some of the light. And if something blocks some of the light, you can look at that light curve and you can try to infer what's doing that. And in some cases, that will be a planet that's eclipsed that star. And so you can then use that to infer the size of that planet. If you know something about the properties of the star, you can then say something about the properties of the planet. I'll just play it one more time. And so this has been a very successful method for detecting exoplanets. If you're looking from the ground, so one of the sort of most successful for a long time was a project called SuperWASP, where WASP stands for Wide Angle Search for Planets. St. Andrews University is one of the leaders in this. And in fact, they initially bought, it's basically professional camera lenses because they have a very wide angle. So you can search a large patch of the sky. And they initially bought the camera lenses off eBay because they couldn't find them any other way. And roughly speaking, if a Jupiter-sized planet passes in front of a sun-like star, it blocks about 1% of the light. So this little figure on the left here is meant to show a particular system where this is the brightness of the star, and it drops by 1.5% when this roughly Jupiter-sized object passes in front of the star. If you're looking for something Earth size or Earth radius, then you're looking at about a 0.01% dip, and you really can't do that from the ground. The ground-based telescopes aren't good enough to see that kind of dip, but you can do it from space. And Kepler was one of NASA's satellites that operated until a couple of years ago, and TESS, which is the Transiting Exoplanet Survey satellite, which is a more recent one that's been operating for a little while now, and they can do this. So you can now detect these dips or these transits where the planets, of order the size of the Earth. So rather than 1% blocking 1% of the light, you're blocking something like 0.01% of the light. But as I said, that gives you some idea of the size of the planet. If you know the size of the star, you know what fraction of the light's blocked. You can estimate the radius of the planet from the radius of the star. But it doesn't tell you much, say, about the mass. And so to do that, you can use another technique, which is actually the one that I do most of my work on.
Can I interrupt you, Ken?
Yeah,
We've
sure.
got a question here from George. How much of a dip in intensity do sunspots produce?
Good question. So they do produce small dips. I can't give you an exact number. Probably some of them are about the size of the Earth, but they're not completely black. So they're not going to block as much light. But they're very variable. So the thing about this method is that you don't look for one transit, you look for many. And then you see the periodicity. And sunspots typically won't last for enough rotation periods for it to produce many, many dips. So they're not likely to mimic a planetary transit. Having said that, there are other things that do. So there are quite a lot of false positives here. But one thing that helps you, if you look at this one on the left, it's not completely flat at the bottom. And that's because the edges of a star are slightly darker than the center. It's a thing called limb darkening. It's basically an opacity effect. And so if you see this kind of shape, then you know that it's something that initially crossed the edge of the star and then got to the center of the star and then went back out again. And so there are characteristic features of these transit signals that allow you to tell whether it's a a planet or something else. But I think that sunspots are not enough of a change in brightness to really be a big problem for these. But there are other things that are. Is that all right? Okay, so the other one is the Doppler wobble method, and that uses the fact that if you're in a planetary system, even in the solar system, technically all of the planets and the star orbit the center of mass of the system. And so if you stare at the star, you can measure its spectrum, but as it's going around the center of mass, due to the gravitational influence of the planets, the star will at times be moving away from us and at times be coming towards us. And so the spectrum, which will have various spectral lines in it, will shift from moving to the red side when the star's going away to moving to the blue side when the star's coming towards us. And this is just the Doppler effect. It's essentially the same effect that gets used when, you know, a traffic policeman tries to catch you speeding. And so you can determine the line of sight or the radial velocity of the star. And if it varies sinusoidally or periodically, then you can infer that there must be something orbiting that star. And you can then say something about the mass of that object. And so this is one of the first ones detected, which was a Jupiter-like planet orbiting a sun-like star. And you can see that the velocity of the star varies from coming towards us at around about 50 meters per second to going away from us at around about 50 meters per second. And for comparison, Jupiter induces a velocity of about 13 meters per second on the sun. So this is slightly bigger than the effect of Jupiter on the sun. But this planet is much, much closer. So it's actually orbiting with a period of only 4 days. So it's quite a large signal, and instruments could measure this. This was detected in 1995. So what's that? 25 years ago, relatively easily. But it's a very hot planet orbiting very close to its parent star. So the project I'm involved with is on a telescope in La Palma. This is the bit we built in Edinburgh, is the black box bolted to the sort of side of the back of the telescope. If you can imagine, if you were standing next to that black box in that image, looking to the right, the sort of dish, the mirror is through that wall on the right. And that's our sort of what we call the front end unit. And then the light goes down into a big spectrograph in the basement that measures the spectrum of the star. And then you do that multiple times. It's on an Italian telescope on La Palma, which is the picture down there. And with an instrument like that today, we can now measure stellar radial velocities of only a few meters per second. So we can now detect Earth-sized planets, Earth-mass planets, but very close, very, very close to the parent star. So, you know, this is in fact, it's a 4-planet system. I've shown you 3 of them. 2 of them have nice circular orbits. You can see the sinusoidal variation is quite symmetric. One of them is a bit more eccentric, so the orbit's not quite a circle. The star moves slightly faster at some times than at others. But we can now go down to these really small velocities and radial velocities of the stars and detect quite small planets quite close to the star. And if you want to see where this one is, this particular system, it's called HD 219134. If you go out into the night sky, you can often see Cassiopeia, which looks like a W. And if you go slightly to the right, about a bit bigger than that distance, there's a star there. And that's the star that hosts those 4 planets that we detected 4 or 5 years ago, using the instrument on this telescope in La Palma. And then the whole beauty of this is that if you have the transit measurement from the blocking of the starlight, you can estimate the radius of the planet. If you use the radial velocity method, you can get the mass of the planet. If you put them together, you can then estimate the composition. So you can say, well, what's the composition of a planet that's 5 Earth masses, 1.5 Earth radii? Well, it's going to be very similar to the Earth. So there's the Earth and Venus on this line. Objects, planets with about 30% solid iron nickel cores, 75% magnesium silicate roughly. So that planet's going to be similar to the Earth and Venus in terms of composition. It's very, very hot. It's being much more heavily irradiated by the star than the Earth and Venus are. If you then go up to, say, a more massive one, you can say, well, this must be a planet that still retains some kind of massive hydrogen helium atmosphere. So you can now, with both these mass and radius estimates, you can now actually start to say something about the composition of these planets. I should stress, though, that even though there are quite a lot that have compositions similar to the Earth and Venus, which are down here, this line here would be something with a similar composition. They are much, much closer to their parent star. So they're not Earth-like in terms of having an atmosphere or being able to be habitable. But we are getting to the point where we can now start to determine whether a planet is rocky or whether it still is gaseous like Uranus and Neptune. So I was going to stop at that stage, Chris or James, and that's the few slides I put together about the kind of work I do on detecting exoplanets. So I don't know whether people have some questions about that now.
Yeah, I've got a question. What happened to the planet that turned to dust?
Which one are you thinking of? The Fomalhaut B one, the recent one?
There was a recent one, and people said, "Oh, it's now dust," and nobody said if it turned to dust or it was always dust.
I think it's always been suspicious, and I think people have never quite trusted it. There's obviously a signal there. So that clearly, when you look at the system, there was a bright spot, and the bright spot was clearly moving, but it probably was never a planet. So in fact, we have a journal club next week when somebody's going to present that paper, which I haven't yet had a good look at it. But it's always been one that's never looked quite right. And I've got a funny feeling there was, because often you can see these at different wavelengths, and this one I think was only visible in certain wavelengths, which tells you something about what it actually is. So it's never been one that I think people have been completely confident was actually a planet. But that was directly imaged, right? That's a slightly different thing, which I haven't really discussed. So that was actually seen in an image. So all the ones on this plot are what we would call indirectly detected. So you either find them by how much light they block when they pass in front of the star, or from the wobble of the star as the planet orbits around the star. But you can't actually see these directly because they're too close to their parent stars to actually detect. Whereas the Fomalhaut B one was much wider orbit and was actually directly detected, but it's never been one that's been completely secure.
Okay, we've got two more questions. One is, how can we look at the star with the planet next to Cassiopeia?
Oh, how can you look at? Yeah, so you can't actually see the planets. You can see the star. Maybe you might need a pair of binoculars. So you could just go out into the night sky and try and sort of measure across. Was the question, how can you see the planets?
No, the question was, how do we, to look at that planet next to Cassiopeia, but I interpreted it as to see the star that has the planets.
Yeah, you'd have to go out and sort of orientate this sort of image and then try to work out which of the, because it's still relatively bright. It's quite a bit, and so you'd have to kind of work out which of the stars off sort of in this direction was this one, HD 219134. The planets are way too close in, even so we only detect them indirectly via this radial velocity method. The fact that the star is wobbling around the center of mass tells us there must be a bunch of planets in orbit around it.
So if we go out and look at it and see if it's dimming visibly.
Actually, these ones, oh no, one of them does transit. These were found by radial velocity. So one of them was close enough that it does transit, but it's very small. So these are Earth size. If you remember, if I go back, for an Earth size planet, the dip is like 1/100%. So even we wouldn't see, even for a Jupiter, I don't even think we'd notice a 1% drop with the naked eye. So these are all detected by observing these stars over a long time period and carefully analyzing the light curves to see if there's any periodic dips in brightness. And for something like this one, where the planets are very small, these ones here, the dip would be way too small to see with the naked eye. We actually got time on one of the space telescopes to observe it and did find that one of them transited.
And Bill asks, on your slide with the graph of the planet compositions, what is the Goldilocks zone on this chart?
Oh, we don't have a Goldilocks zone on this chart. And so the Goldilocks zone in exoplanet science would be a planet that is orbiting in a region where it could have liquid water on its surface. So in other words, where it's of that sort of temperature. Now, these are all relatively close. Some of the stars are a bit fainter. So some of them, so this color bar here is telling you how much flux they get relative to the Earth. So the purple ones are ones that are maybe getting a similar level of flux. But I don't think there's anything on this plot where we would regard it as really in some kind of habitable zone. They're all too hot as far as I can, I think. So it's quite tricky to find things in this Goldilocks zone because they tend to be slightly further out.
question from George. Is there any prospect of being able to detect planets that are orbiting in a plane that does not transit its star?
Yeah, so the radial velocity method can do that. So at the moment, so in fact, the very first planets were detected that way. So you just observe stars and try to find ones that appear to have radial velocities that are not that show this periodicity that you can then analyze. The problem there, of course, if it's very, very inclined orbit, then you could have a very massive object that mimics a planet. But in most cases, the ones that we detect are probably planets rather than something much more massive. So you can detect planets just using the radial velocity method for ones that are not transiting.
I suppose the Goldilocks zone, going back to the Goldilocks zone question, that brings you on to the climate of exoplanets. How do you know what their climate is like?
You mean on exoplanets themselves? So there's work going on to do atmospheric characterization of exoplanets. Again, at the moment, so when you have a transiting exoplanet, if it's relatively massive, and by massive I mean Jupiter kind of sized, then the amount of light it blocks will depend on the wavelength at which you observe, because the atmosphere will be transparent or slightly, will let through more light at certain wavelengths than at others. So it'll appear to get slightly smaller or slightly bigger depending on the wavelength. And you can use that to then infer something about the composition of the atmosphere. And then you can do modeling to try to fit to that, to say, what is the composition of this planet's atmosphere. And but at the moment, that's mostly done with really big planets, so Jupiter analogs. Of course, the goal would be to be able to do that for lower mass planets, and some of the upcoming missions might allow us to do that for what we call super Earths. So these are planets that are maybe 5 to 10 times the mass of the Earth and maybe 1.5 to 2 to 2.5 times the radius of the Earth. So they probably still host quite massive atmospheres, so probably not habitable, but it means we're slowly coming down towards being able to try to characterize the atmosphere of something that might be Earth-like.
And a follow-up question on that. With these massive planets, you say they're Earth-like planets, and I think you said they're 10 times the mass of the Earth.
Yep.
Is there any prospect of those having a climate that is actually similar to Earth's?
I don't think so, not for the big ones, for a number of reasons, partly because a lot of them, if you look at this plot, they tend to be up in the top right-hand corner, and that tells us that these are planets that host still quite massive atmospheres. So if you enter the base of those atmospheres, we're very, very high pressure. So it's very unlikely that those would host the kind of atmosphere where we could survive. When you get lower mass, then it becomes more possible. Of course, these ones, again, as I said, are mostly quite hot. So they're, again, probably too hot to host atmospheres. But they do tell us that rocky planets exist. So, that's a step towards trying to find rocky planets at distances where we could have atmospheres that might allow life to exist, or might allow liquid water to exist, and hence life.
So your graph suggests that small planets are very hot and large planets less so. Is that just because of the detection?
Yeah, so that's mostly a selection effect. So you can find the bigger ones more easily when they're further out, because partly because the transit probability depends on the distance. So it's a bit harder to see them when they go further out. But the radial velocity signature is bigger, so you can detect the big ones on wider orbits, so they can be cooler than the small ones, which tend to be much closer in.
A leading question now, your work on exoplanets, what does that lead you to conclude?
Oh, I missed that.
Sorry, that's because I muted myself by mistake, because I'm a klutz at this kind of thing. How does your work on exoplanets lead you to understand climate on Earth and be interested in climate change?
So I guess, that was kind of fortuitous, but a lot of the background physics is very similar, right? It's atmospheric physics. And in fact, a lot of physicists, I think, have a background that allows them to understand a lot, because a lot of quite a lot of the basics of climate science is just physics. Of course, there are lots of oceanographers and paleontologists and all sorts of other people studying the climate and how it's evolved over time and things like that. But the basics of climate science is still sort of firmly embedded in physics. So I think that was mostly what I think got me into thinking about climate science. But partly as well, when you look for exoplanets, you start to realize just how, well, they're very common, but the conditions for life appear not to be as common. And so it feels a bit unfortunate that we seem to be rather blasé about how we're impacting the habitability of our own planet. Not that I think we're going to make it uninhabitable, but we're certainly changing the one of the key ingredients for making it habitable, which seems like a risk we should maybe be taking slightly more seriously.
We'll have a brief pause while all of the climate scientists, ecologists, environmentalists rage at us for saying it's just physics. But
well, I was trying to say not just physics, but the underpinning science is physics. Of course, there's an awful lot of detail, and there's an awful lot of other areas of science that, as you say, ecology and oceanography and paleontology and all sorts of things that sort of come into the climate context. But you know, the basics of the greenhouse effect and that is largely physics.
There is only physics. All the rest is stamp collecting, Rutherford. George asks, what is the typical age of stars that have been observed to have exoplanets?
And are they wide-ranging? Everything from hundreds of millions. Well, when they're too young, it's very hard to find them. So we think planets form with stars. So technically, there are planets around stars that have just formed. There are certainly some we found observed around stars that are, tens. What's the matter? Oh dear. Everything all right?
Yes. It's outside.
What did he do?
He set an egg carton on fire.
Oh dear. Okay. Sorry. My son was cooking dinner and has managed to set something in the kitchen on fire, but the family sorted it out. Okay.
Oh, I'm glad you're okay.
Yeah.
These moments are what make Zoom meetings brilliant.
Okay. Anyway, so I've lost track of what I was saying there, I'm afraid.
You were asked what is the typical age of stars that have been observed to have exoplanets.
Yeah, sorry. So everything. So planets form form at the same time as stars, so they're there at the beginning, and and they basically survive the entire lifetime of the stars. So a sun-like star will live for 12 billion years. So we found planets around stars that are hundreds of millions of years old, billions of years old, 10 billion years old, the whole range of ages. Our own sun is 4.5 billion years old. So there's no age dependence as such, other than some stars have longer lifetimes than others.
And Bill thanks you for proving that it is in fact a live session.
Yes, that's exactly it.
Okay, we don't have any further questions. I'll just give a moment if any come in. Yeah, I can hear the dialogue going on in the background, but I can't make out what she's saying, but I'm sure it's very interesting.
I'd put some climate slides together if you want me to show them and then see what that leads to.
Yes, please, if you would.
Yeah, sure. Okay. So as Chris mentioned, we're mostly interactive on social media through the climate stuff I do. And so I got interested in sort of science communication, I guess, is one way to put it, and specifically climate science, partly because I came across various sites that seem to present rather sort of incorrect interpretations of climate science. So I started getting involved in sort of writing publicly about climate science. And partly, as I mentioned earlier, the physics, the underlying stuff is basically just physics, the greenhouse effect. So, you've got energy coming in from the sun, some is reflected, some is absorbed by the surface and in the atmosphere, and then these energy going back out again. And in order for the planet to be in energy balance, the amount leaving the top of the atmosphere has to match the amount coming in. But because of the greenhouse gases in the atmosphere, mostly, carbon dioxide, water vapor, methane, the energy radiated from the surface can't escape directly to space. And so consequently, the surface ends up being about 30 degrees warmer than it would be without an atmosphere, and that's what we call this planetary greenhouse effect. And CO2 is important because it's the dominant non-precipitating greenhouse gas, so it's sometimes called the control knob. So water vapor precipitates, but CO2 doesn't. So once it's in the atmosphere, it warms everything up and causes this long-lived greenhouse effect. Then the reason climate science is important because we are enhancing this greenhouse effect. So as we add atmospheric CO2 or CO2 to the atmosphere, you cause the surface to warm. And the basic physics could be that what's happening is you're increasing the altitude in the atmosphere at which energy escapes to space. And that then forces everything below that altitude to warm up in order for the system to remain in energy balance, right? Because if it didn't warm up, we'd have less energy leaving the top of the atmosphere than coming in. And hence, we would warm up in order to retain energy balance. And roughly speaking, we expect there to be about 3 degrees of warming every time we double atmospheric CO2. And to date, what we've done is increased it from around about 270, 280 parts per million that it sat at for thousands of years to just over 400. And we've done that in about 100 to 150 years. And it's very definitely us. And there are lots of indicators of this. You can observe that the surface is getting warmer. You can measure the heat in the oceans and see it rising. You can see the Arctic summer sea ice decreasing. You can see that the ice mass in Greenland and the Antarctic is going down, and you can observe sea level rising, which is partly a combination of increasing ocean heat content and partly a reduction in ice mass of the mass of the ice sheets. And so, you know, I guess this all seemed fairly straightforward to me when I first started thinking about this. And I was very surprised that there were so many sites that seemed to dispute a lot of this. And I thought it would be straightforward to try to explain why it is such an obvious and basic thing. And I was horribly wrong, because science communication on this sort of contentious topic turns out to be quite complicated. And that's all I was going to say about that. Just a few more slides on that. So
it's very interesting on the science communication, isn't it?
yes,
It's not as easy as one thinks it should be.
It's not at all. Yeah.
Okay, we've got a couple of questions there. One refers back to your exoplanets, and that's from Barb. Barb asks, do you believe that moons are more likely to have life than planets?
I don't know if I believe that. So there's certainly people looking at that, and there are attempts to detect moons around planets. I don't think we've ever done it, but they think that you could see small variations in the timing of a transit that might tell you if there's a moon orbiting around that planet. And certainly people say, well, if you had a big planet like Jupiter orbiting in the Goldilocks zone or the habitable zone, and then around that was a moon that was maybe big enough to have an atmosphere, maybe you could have life on the moon. So the people are taking that seriously. But in the solar system, we don't know of any moons that are big enough to retain an Earth-like atmosphere. So it's not, we don't yet have evidence that such moons could exist, but certainly it's something people do consider and do think is a possibility.
Thank you. And David asks, how do we know what the CO2 level was before we measured it?
It depends what you mean by measured. So they can take ice cores and there's CO2 trapped in bubbles in the ice. And so they can track it back all the way back to about 1 million years ago, I think. And various other, what they call proxy methods of doing it. So that's sort of the main way that I'm aware of that people can measure CO2 levels going back thousands or hundreds of thousands of years.
And slightly off topic, and going back to your talking about science communication, and particularly on social media, how have you found that?
It's very, I found it very stressful initially, and I probably should have stopped because it wasn't probably good for me. You do learn a little bit how to do it. I don't know that it's been effective. It's very hard because the people that you maybe end up sort of directly interacting with tend to be people with strong views, and often those discussions don't go very well. I don't know what impact it has on other people who might observe it. But yes, I still haven't quite come to a good conclusion as to what works or what doesn't work or what's effective and what isn't, because it is such a difficult environment when you're trying to discuss something quite contentious.
Okay, and we have a question here from Bill. It's a longish question. James, I need assistance from my organizer here. He's probably having a quick sip of whiskey or something. James, are you there? Right, let me see if I can do it myself. Bill,
I'm here.
Okay, I was going to ask if you could bring Bill Corney in as a panelist. I've actually found the button so I could do it myself if you like now.
Bill, if you're happy with that, if you just click the raise hand button and then we'll bring you in. There you go. You've got the button, you can do it.
I have the power and I have brought Bill into the conversation. Go ahead, Bill.
Hello, can you hear me?
Yes, we can.
Hello. I don't have my video camera on, which you'll be relieved by. So my question was, I mean, I'm undergraduate level many moons ago, late 80s, 90s. I did study paleoclimatology as one of my course subjects, and I recall from the time there were lots of other factors that were considered influential in climate change. So, you know, natural cycles of volcanism, natural cycles of changes in solar output, you know, the Earth tilt varies, you know, you have the effects of continental drift and the movements of the various plates, the eccentricity of Earth's orbit varies, you know, ice albedo, etc., etc. So there was many other sort of physical factors which influenced climate change. My question was, have the latest, to what extent have the latest climate studies been able to separate out these kind of factors from the, I guess, the physics-based impact of the man-made carbon loading into the atmosphere?
So pretty much, I mean, everything's got uncertainty. So things like Earth's orbital variations, they play a key role in Milankovitch cycles. Yeah. The period of the Milankovitch cycles are hundreds of thousands of years, or tens of thousands of years, right? So they're very slow, and so something like that really can't explain the warming in the last century. So it explains why we go into and out of glacial periods, but it doesn't. It can't explain the last century. The sun, well, yeah, for a while the sun was getting slightly brighter, but it's been getting fainter very slightly for the last few decades. So it can't explain why we've got warmer. Volcanoes certainly play a role, and you can see that in the temperature record. In fact, I'll go back. You can see them sort of maybe this is too smoothed out, but 92, there was a volcano. I think it might be that one. And so they certainly play a role, but volcanoes tend to make things slightly cooler for a couple of years, and then everything precipitates out. Ice albedo, yeah, but that tends to be more of a feedback. That's a response to some change. So if the sun gets a bit brighter, it might melt some of the ice, and then that plays an amplifying role. So pretty much all of these alternatives have been looked at really closely, and so they do play a role in climate change on different timescales, and maybe a small amount in the past century. But the dominant, I mean, it's pretty clear that the dominant factor in the most recent warming is the increase in atmospheric greenhouse gases that we've done, right? So you're quite right that there's lots of other factors that can play a role in changing the climate, but none of those are really able to explain the modern warming, is what they refer, what they think about.
Thank you very much, Bill. I'm going to ask you to explain two slightly jargon terms. First, ice albedo.
Yeah. So that's just how much, so albedo is just how much is reflected. So typically, if you go back to this figure here, I mean, we reflect about 30% of the incoming sunlight. So we refer to the Earth having an albedo of about 0.3. So 30% is reflected. So ice albedo just refers to how much is reflected by the ice. And so, of course, if you change the amount of ice on the planet, then you change how much is reflected, which then changes how much energy we're getting from the sun, and then either warms or cools depending on whether or not you've increased the amount of ice and hence increased the ice albedo, or reduced the amount and hence reduced the ice albedo. But that tends to be a feedback, what we think of as a feedback. It's a response to some other effect. So it's unlikely that something like that would just happen by itself. So the fact that we're increasing atmospheric CO2, it's warming the planet, it is changing the albedo of the ice, but that's a response to our our actions rather than a driver of the warming.
Thank you. And I have to ask you about the Milankovitch cycles
Yes.
to explain what they
Yeah.
are.
So Milankovitch, I don't have a slide for that one. Milankovitch is a name, so it's a person's name, and it's these glacial cycles where the Earth will be cold for, and I forget the exact amount of time, tens of thousands of years, big ice sheets that cover large parts of North America and Europe, and then we'll switch over a period of maybe 10,000 years into a much warmer phase, which would be an interglacial period where the ice sheets retreat. And we're currently in an interglacial, so we do still have ice sheets. We've got the Greenland ice sheet and the Antarctic ice sheet. So we're at a warm period at the moment, and we should have been cooling very slowly back towards another glacial period, but we're not. We're, of course, going in the other direction now. But the Milankovitch cycles are, I should be a bit more specific, the Milankovitch cycles actually refer to, more specifically, the very small variations in the Earth's orbit around the sun, driven primarily by the outer giant planets. So the Earth's orbit is not quite a circle, it's very slightly eccentric, and the influence of the outer planets causes the orbit to change very slightly, very slowly over the course of many thousands of years. But those very small changes are enough, or were enough, to trigger us from going into a glacial period and then out of a glacial period that happened every 40 or 50,000 years, if I remember correctly.
Thank you. Marion asks, can we tell how much benefit in terms of slowing climate change various actions might affect the outcomes? For example, planting trees, ceasing farming livestock, using clean energy.
It depends what that's a tricky question. So if we want, so pretty much the science at the moment, and I think this is largely agreed, is that if we wanted to stop, so in other words, we want to stop warming the planet, then we have to get net emissions to zero. So we've got to stop emitting CO2 and methane into the atmosphere. Now, you can do that in many, many ways, right? You could find ways to capture it. So you could just keep using fossil fuels and you could capture the CO2 and store it, and that would work. Technologically challenging, we don't have that at scale, but it's one possibility. You can, of course, plant trees that will take up some CO2, but there's a limit because we've already exact numbers are about a quarter of what we've emitted in the last century is a consequence of changing the land, right? Of essentially cutting down trees and changing how we use the land. So if we did as much tree planting as we could possibly do, we'd probably only reverse a maximum of a quarter of what we've already done. And so it can't be a major way of getting all of the emissions to zero. Of course, if we emit less, if we use more public transport, if we use electric vehicles, if we put up renewables or nuclear or whatever else we use, it all has an impact. But in some sense, the long-term goal, if you like, the way we will get the climate change to eventually stop is to eventually get our emissions to zero. And that's going to take a whole, as far as I can tell, a whole combination of different changes.
Okay, and George homes in laser-like on a detail. What does the red -2 indicate in your greenhouse effect
good question.
slide?
Let me see if I can work that out. I think I probably don't know the answer to that. It's probably in the paper. It's probably relating to the way something might have changed in this particular paper. So
George wins an extra point for that.
Yeah, that's right. So I don't know exactly what the -2 refers to there. It's probably explained in the figure caption that I haven't put on this slide.
It's always good for a scientist to say, I don't know. I do that a lot.
I do it all.
Okay, Juan, you have a question. Can I ask you to raise your hand if you would be willing to ask that question live? And we wait for Juan. Otherwise, I'll read it for you. That's just funny because the raise your hand doesn't have a no, I'm not raising my hand thing.
Yeah.
Juan asks, do you think that it is important to study exoplanets that are around O and B stars? And for me, would you explain what an O and B star is?
So O and B stars are very, very massive stars. So 10 or more times the mass of the sun. And the answer to the question is it would be wonderful, but they have such short lives, it's virtually impossible. So the sun has a lifetime of maybe 12 billion years, and O star might have a lifetime of 10 million years. So it will essentially form and explode in a supernova almost straight away by our standards. And so they're very young. They're always very young. They're always in star forming regions. They're very hard to do any kind of the kind of observations you'd need to do to try and even see if they had a planet around them. So we just don't really know if they have planets, and clearly the lifetime of the star is so short that that planet doesn't exist for particularly long. So it's not something we've really considered.
Okay, we have one more question, and I'll just take one or two more because then we can close down in time for the applause for our health service and key workers that we always do at 8 o'clock. This is also from George. If the coronavirus lockdown continued indefinitely, what effect might that have on climate change?
Well, so the projections for this year are we will emit 5% less than we would have done. So that has a very small effect. But climate change is cumulative, so it's not a 5% effect. It will mean that we'll be very slightly cooler than we would have done. If it carried it indefinitely, I don't know. I mean, presumably, yes. It's not. It doesn't feel to me like a particularly viable solution to climate change, right? Because we don't really want to solve climate change by shutting everything off. We want to, I think, ideally solve it by finding ways to do the things we've always done, but without having this impact on the climate. So, but even if I guess even if we were forced to reduce our activities, we'd still have things happening. So we'd still be heating our homes, we'd still be, having things delivered, we'd still be, in some cases going to work. So it would have a small effect, but I think it would mostly be modest. And as I say, not the ideal way to be solving climate change, I think.
Okay, thank you very much indeed, Ken. The way we applaud here is by raising and lowering our hands, which is rather muted, but it's a way of doing it. I'd like to thank Ken very much indeed for, I'll unmute myself here. Am I on Spotlight now, James? Or I can do that to myself. No, I can't. Yes, I can. There we are. Hello. I'm just getting used to this hosting business. It's quite interesting. I'd like to thank Ken very much indeed for talking. And I'd just like to point out that all the speakers at all Cafe Size are volunteers. They do it because they enjoy doing it, because they want to share. The fact that maybe someone asked them to do it is almost irrelevant because the responses are almost universally incredibly enthusiastic. So thank you very much for giving us your time and a very interesting exposition there. I'd like to point out Cafe Sci is free to attend. If you do a live Cafe Sci, you never have to pay to go to it. It's not a fundraising or money spinning event at all. And these are also free, but you can make a donation which might go towards buying a drink for the speaker or something like that if you feel like it. And a few people do that. They do that by registering on the Eventbrite page and just choosing to whom. That's not very significant. And I'd also like to James initiative our lucky enough first cafe and we have them lined up into the future, and that's really James's initiative in doing it. And he also makes sure that these things are live streamed to other services like Facebook, I think YouTube, Twitch, and various things that I don't know about, and they're recorded, and quite a lot of people do watch them after the event, although I'd recommend tune in and watch it live because it's much more fun, because you can have, I'm on the whiskey now. Coming up, oh, did someone say I've frozen? You've frozen and I couldn't hear how to donate, Avril said. Can anybody hear me?
Yeah, you're back on again. It just was a few seconds.
Yeah. Avril couldn't hear how to donate. It's all right, Avril. You'll find out when you register on an Eventbrite. You have a choice of paying a small amount for the ticket, and I think it's £2 or £3 or something like that. Coming up, we have, and I did have a list of these coming events. We're on a bit of an astronomy roll at the moment. So next week, we have Jennifer Millard, who's talking about the hidden universe. So she's taking us on a tour of radio astronomy and how we look for the things that we can't see. And that's quite dear to my heart because I've been using microwaves to image inside the human body. And it's basically a similar thing to using microwaves to make an image of the universe. As Ken says, it's just physics, everything is. And then after that, we've got Eloise, and she's going to be talking about exploding stars and core collapse. So that's in terms of supernovae and black holes. Lastly, I'd like to thank you, the audience, for turning up and attending. It makes it very different if you've got people live asking questions and interacting. It's nice to know that you're all out there. I hope you all keep safe and well. And I'd like to thank you and look forward to meeting you all again next week. So goodbye from me and goodbye from him.
Thank you very much.